So we're going to look at how to derive the wave equation based on vibrations in a string. So suppose we've got the equilibrium position of the string here, and then the string when it's displaced upwards is here. This is supposed to be sort of more curved and bent. And we're going to take our state variable to be the displacement profile of the string at time t. So in other words, the graph of this function is going to exactly be the geometry of the string when the way it's displaced. And so u is going to be the vertical amount. So this distance right here is u. So what we're going to do is set up a PDE for u by balancing tension forces on this segment. And so we'll do that by using Newton's second law and the principle of mass balance. So here's the idea. So for tension forces, let's say we'll have T is going to be the force due to tension. And since this is a vector, this is going to be the force to the right at some particle at location x. So suppose we've got some segment here, and so here's from, say, A to B, and this is a zoomed close-up on some much bigger string, so let's just say it's looking something like this. So over here at this end, we've got some tension force, and we assume it's tangent to the string itself. So there'll be a tension force right here that looks like T a time. And then here there'll be one, and it'll also be tangent to the direction of the string itself. So this force will be TB at time t. And then at any given point here, so we've got our, our force, and it's being directed with an angle. So this angle right here, maybe I'll give that a different color. Let's make it purple. Okay, so this angle right here is going to be theta at time t. And so it should be clear that based on what I said about how the u is giving us the displacement, then we know that this angle here is going to coincide with u sub x. Okay, the slope of that curve at that point. Okay, so let's see. So we're going to make the assumption. So this is just going to be for the case when there's a small displacement. And so this means that, for example, displacement is vertical only. So to give you an idea of what we are ruling out, you can imagine some situation where the string is, say, really displaced strongly, something like this. And then if you look at what happens to a particular little particle of it, well, it might get displaced straight up, or it might get displaced over to the side a bit, and that amount could vary by depending on how far it is to the right. So we might have something that looks kind of like this. Anyways, we are going to not consider this model because it is nonlinear and more difficult. So if you're doing vibrations with a large displacement, you have to come back and work out a more complicated model. So let's not do that. Okay, so implications. Of this assumption. So implication number one is what we're going to call the mass balance principle. And so the idea of mass balance is that the mass of the string over some interval, so some little interval AB, remains constant. Now the density at a particular point may change. So the density will be given in units of mass per length. The density may change because if you have something which is in equilibrium position, it will have some length. But if you have something that has been stretched, then it will have some longer length. And so it will have a lower density. So it's quite reasonable to expect that the density would be changing with respect. Anyways, so let's see. So in terms of equations, what the mass balance principle means is that if we look at the total mass over the interval from A to B, so this is going to be, you find the total by integrating the density, and it's over an interval of a different length now, so we need to actually do the arc length integral. So we've got 1 plus the derivative squared, square rooted. So here we are going back to that figure, we're looking at some little triangle here on the curve that we're integrating with respect to. And so that gives us our arc length formulation for this guy. So that's the total mass then between A and B in the stretched version. And this should be equal to the total mass between A and B in the equilibrium version. And so I'll call it the equilibrium version rho 0. And so this is some equation that holds for all A and B. And then just like we saw in the derivation of the diffusion equation or the heat equation, since it's true for any A and B, we can actually remove the integral and actually let me just tidy that up and there we go. And so we have this equation. Okay. So on the other hand, we also have another implication, and this is that horizontal forces balance. Because if the horizontal forces did not balance, then the greater force in one direction would have pulled the particle in that direction, and it would not have gone straight up, it would have gone to the side instead. Okay, so what does it mean for horizontal forces to balance? That means at the left and right endpoint of our small interval AB, we have that the horizontal component of TB or the horizontal component of the force at x is equal to the horizontal component of the force at A. And this again is true for any A and B. And since that's true anywhere on the interval, then we can similarly conclude that it has to be constant all the way through. So we'll call this constant value of the tension tau. Okay, so tau will change over time because it'll be more taut when it's displaced from equilibrium. But from left to right, it does not change. Okay, so in the next clip, we'll look at how to use these principles to derive the wave equation.